Hello and welcome back to another deep dive. So today we're actually going to open up the chemistry textbook.
We are indeed. And specifically, Unit 2.
Exactly. And we're going to tackle a topic that, it literally powers our modern world.
It really does. If you're listening to this on a phone, a laptop, or, through wireless headphones, you're using the very technology we are about to discuss.
Yes. We are diving into galvanic cells. Now, I've gone through the notes, the insert chapters, all the reference materials you sent, and I want to start with something physical.
Good.
Because chemistry can sometimes feel like just, equations on a page, but this starts with a very real, very observable thing you can see in a lab.
Correct. We should always start with what we can actually see. Science begins with observation, after all.
So looking at the source material, let's set the scene. Imagine we are in the chemistry lab. On the bench, we have that classic setup. There's a beaker. It's got a blue solution in it. That's copper sulfate. And inside that, there's a copper rod. Then next to it, another beaker, this one with a colorless solution, zinc sulfate, and a zinc rod.
This is the Daniel cell. It's the standard setup. Most Class 12 students will see a diagram of this on page 1 or 2 of the electrochemistry chapter.
Right. So now you take a wire and you connect these two metal rods. Maybe you put a small voltmeter in the middle to see what's happening. And at first, well, it looks like nothing is moving. It's all just static.
It seems that way.
But if you leave it for a couple of hours and come back, things have physically changed.
Yes, and the changes are quite dramatic if you look closely.
The blue color of that copper solution, it starts to fade. It gets much paler. And the zinc rod, that solid metal stick, it actually gets thinner. It looks like something has been eating it away. And then the copper rod in the other beaker, it gets thicker. You can see a fresh layer of that reddish-brown metal deposited on it.
It's almost as if the zinc is, teleporting its mass over to the copper side.
Exactly. And the big question is, why? All we did was connect a wire. Why did the blue color fade? Why did the zinc rod corrode? And most importantly, why did the needle in the voltmeter move?
That why is the absolute essence of electrochemistry. What you're witnessing there is the conversion of chemical energy directly into electrical energy.
So for our listener today, whether they're a Class 12 student prepping for the board exams or just someone curious about how things work, what's the big takeaway here?
The big takeaway is that a galvanic cell is the secret sauce behind every single battery, from the small AA battery in your clock to the huge lithium-ion block in an electric car.
Wow.
It explains why some metals produce a voltage and, on the flip side, why your batteries eventually die.
Okay, so let's unpack this mechanism. I want to start at what we call the zero-level explanation. Let's forget the equations, forget the numericals for a second. Why does just connecting a piece of zinc to a piece of copper make electricity happen?
At the most fundamental level, you have to understand that electrons are, well, let's just say they're a bit opinionated. They have preferences.
Preferences, like they actually prefer one metal over another.
Yes, exactly. Different metals hold on to their electrons with different strengths. Zinc, for instance, is a very generous metal. It loves to lose electrons.
Okay.
And copper, or more accurately, the copper ions in the solution, they are much more eager to gain electrons.
So it's a difference in potential. One side wants to give, the other wants to take.
Precisely. A galvanic cell is just a system where we let electrons do what they naturally want to do. They want to leave the zinc and just rush over to the copper.
I like that phrasing. They want to move. It's not being forced.
That is the most important word. Spontaneous. If you remember nothing else from today, remember that word. In thermodynamics, we talk about Gibbs free energy, right? That delta G value that everyone worries about.
Oh, right. Delta G, yeah.
For a galvanic cell, the reaction is spontaneous. That means delta G is negative. The system is releasing energy all on its own. It's creating electricity.
Okay, so let's visualize this. I want our listener to maybe close their eyes for a second, unless you're driving, of course, and picture those two beakers. You connect the wire, and suddenly you have this crowd of electrons acting like commuters during rush hour. They are sprinting away from the zinc station, running through that wire, desperate to get to the copper station.
And that rush, that flow through the wire, that is your electric current. That's what lights up the bulb or powers your phone.
But here's where I always had a doubt in school. Why do they need the wire? Why don't the electrons just, swim through the solution? If both beakers have liquid, can't they just jump across?
That is a brilliant question. It really gets to the core of how this works. And the answer is, well, electrons can't swim.
They can't swim.
Not in this context, no. Electrons flow beautifully through metals. That's metallic conduction.
Okay.
But they don't move freely through the liquid electrolyte. In the solution, the current is carried by ions, not free electrons. So the wire is the only highway available for them.
Okay, that makes sense. So let's zoom in a bit to the molecular level. This is where the board exams will really test us. We need to be precise about who is doing what.
Right. Let's start at the zinc side. We said zinc is generous.
Right, it wants to lose electrons.
So a zinc atom on the solid rod, it decides to leave. It sheds 2 electrons, leaves them behind on the metal rod, and the atom itself just jumps into the water as a Zn2 plus ion.
As the solid metal is literally dissolving into the liquid. That explains why the zinc rod gets thinner. It's falling apart atom by atom.
Exactly. And this process, the loss of electrons, is called oxidation. And the electrode where oxidation happens is always called the anode.
Okay. Oxidation at the anode. And because the zinc atoms left their negative electrons behind, the rod itself becomes negatively charged.
Correct, which makes the anode the negative pole in a galvanic cell.
Got it. Now, those abandoned electrons, they travel through the wire.
We travel all the way through the external circuit, maybe do some work on the way, and they arrive at the copper rod.
And what happens when they get there?
So now we look at the blue solution. It's full of copper ions, Q2+. These ions are just swimming around, and they're missing 2 electrons. Suddenly, they see a whole bunch of electrons arriving on the copper rod.
It's like a reunion.
It is. The copper ions swim up to the rod, they grab 2 electrons each, and they turn back into solid, neutral copper metal. They just deposit themselves right onto the rod.
And that explains why the copper rod gets thicker, and the blue color fades because the copper ions are leaving the solution.
Yes. And gaining electrons is called reduction. The electrode where reduction happens is called the cathode.
So simple rule. Oxidation at the anode, reduction at the cathode.
Always, and the electrons are flowing from anode to cathode.
Okay, before we move on, I want to clarify a definition. Because in the exam, if a student is asked what is a galvanic cell, they can't just write, it's a beaker with wires.
Yep.
We need that proper insert-safe definition.
You're absolutely right. For the exam, if you need a definition, write this. A galvanic cell is an electrochemical cell in which a spontaneous redox reaction produces electrical energy.
Let me repeat that. A spontaneous redox reaction produces electrical energy.
Every word there is important. Redox, because you have both reduction and oxidation. Spontaneous, because it happens on its own, delta G is negative. And produces, because it's a source of energy.
And this leads to a huge point of confusion, right? The difference between a galvanic and an electrolytic cell.
Oh, massive confusion. Students mix these up all the time. The names sound a bit similar, I suppose.
So how do we keep them separate in our heads?
Think of it this way. A galvanic cell is a generator. It creates electricity. An electrolytic cell is a consumer. You have to plug an electrolytic cell into a power source to force a reaction that does not want to happen.
Ah, okay. So galvanic is downhill, it's natural. Electrolytic is uphill, you have to push it.
Perfect analogy. Galvanic is spontaneous. Electrolytic is non-spontaneous.
Speaking of downhill, that brings us to the analogies. You know I love a good analogy to make these things stick. In the notes, you mentioned a ski slope.
Yes. For me, this is the best way to understand why the electrons move. Imagine a ski resort.
Okay, I'm picturing it. Snow, a high mountain.
The zinc anode is the very top of that mountain. It has high potential energy. And the electrons, they're the skiers.
And naturally, skiers just want to go downhill.
Exactly. Gravity pulls them. They don't need a motor or anything to go down. They just slide. In our cell, the potential difference, the voltage, it acts just like gravity. It pulls the electrons from the high potential zinc side down to the lower potential copper side.
But as they slide down, we can put something in their way to use that energy.
Precisely. If you put a little turbine on the ski slope, the skiers would spin it as they went past. In our case, that turbine is your light bulb or your phone's processor. The energy comes from that drop in potential.
That is really, really clear. So a 1.5-volt battery basically has a steeper slope than a 1-volt battery.
In a way, yes. A higher voltage means there's a greater push, a greater difference in potential between the top and the bottom of the slope.
Now, there is one component we kind of skipped over in our mental movie, but looking at any diagram, it's huge. I'm talking about the salt bridge, that U-shaped tube connecting the 2 beakers.
Ah, the salt bridge. The unsung hero of the galvanic cell.
Why is it so important? I mean, if I just took it out, would the cell stop working?
Instantly. The current would drop to 0 immediately.
But why? If the electrons are happily going through the wire, why do we need this other tube in the liquid?
It's all because of electrical neutrality. This is a concept that students often miss. Let's go back to our mental movie. Zinc ions are jumping into the solution, right?
Right. Positive Zn2 plus ions.
So the solution on the zinc side is getting more and more positive. It's building up a positive charge because of all these new ions.
Okay.
And on the copper side, the positive copper ions are leaving the solution to become solid metal. So that solution is left with extra negative sulfate ions. It's becoming negatively charged.
So one beaker is turning positive and the other is turning negative.
Exactly. And electrons are negative. If the zinc beaker becomes too positive, it will physically pull those negative electrons back. It won't let them leave through the wire anymore. It basically says, hey, stay here. We need your negative charge to balance us out.
I see. So the flow just gets choked off because the charge imbalance creates a kind of traffic jam.
Perfectly put. That's where the salt bridge comes in. It's filled with an inert electrolyte, like potassium chloride, usually in a jelly, like agar-agar. It works by pumping negative ions into the zinc beaker to neutralize that excess positive charge.
And positive ions to the other side.
And it sends positive ions to the copper side to neutralize the excess negative charge there.
So it just keeps the books balanced on both sides.
It maintains electrical neutrality and completes the internal circuit. Without the salt bridge, the circuit is broken and nothing works.
That's a crucial point for the exam. If they ask about the function of the salt bridge, the keywords are complete the internal circuit and maintain electrical neutrality.
Write that down verbatim. You will get full marks.
Okay, we've covered the beakers, but I don't carry beakers around in my pocket. Let's talk about the actual battery I put in my TV remote. Is that really a galvanic cell?
It is exactly the same principle, just packaged much more cleverly. We call them dry cells, but the chemistry inside is purely galvanic.
So what's actually inside that little metal can?
In a standard alkaline battery, the metal casing itself is the zinc. The can is the anode.
Wait a minute, the container is the fuel.
Yes, the zinc casing is the anode, and it gets oxidized. Inside, you have a paste, which includes manganese dioxide, and that acts as the cathode. When you snap that battery into your remote, you're completing the circuit.
And the zinc casing just starts to lose electrons and dissolve.
It literally corrodes. In fact, if you've ever left old batteries in a device for too long, have you noticed they sometimes leak that sticky white stuff?
Yeah, and it ruins the remote. I hate that.
Well, that happens because the zinc casing has been eaten away by the reaction. Got so thin that holes appeared, and the chemical paste from inside just leaked out.
Wow. I never realized that the battery is physically consuming itself just to power my device.
It is a sacrifice.
Yeah.
You are trading matter for energy.
This brings up a sort of a philosophical question, but also a practical one. Why does the battery die? I mean, atoms are atoms. Why can't they just keep reacting forever?
That is a very common naive assumption. We tend to think that atoms are infinite, but you have to remember the fuel tank concept.
Like petrol in a car.
Exactly. A galvanic cell isn't creating energy out of thin air. It's converting stored chemical energy. The zinc is the fuel. The electrolyte is the fuel. Once the zinc is all dissolved or the concentration of the ions evens out, the reaction reaches equilibrium.
And equilibrium means?
No more potential difference. The ski slope is now completely flat. The electrons have no reason to move anymore. The battery is dead.
That's a powerful image. A dead battery is just a system that has finally found its balance.
Poetically put, but yes. It has no more free energy to give. Delta G becomes zero.
Okay, this is all fascinating, but we need to make sure our listeners are totally ready to score on this. Let's do a clarity check. I want to summarize the absolute must-know facts for the board exams. Let's call them the 4 golden rules of galvanic cells.
Okay, good idea. Get your pens ready. Or open your notes app.
Rule number 1.
In a galvanic cell, the anode is negative and the cathode is positive.
Anode negative, cathode positive. This is crucial because why?
Because in electrolytic cells, it is the exact opposite. So for galvanic, just remember, the anode is the source of all the electrons, so it has to be negative.
I've heard there's a mnemonic LOAN that's used for this.
Yes, that is a classic, LOAN. If you draw the diagram in the standard way, the anode is on the left, oxidation happens there, it is the anode, and it is negative.
LOAN, I like that. Left, oxidation, anode, negative. Okay. Rule number 2.
Electrons always flow from anode to cathode.
A to C, like alphabetical order.
In this case, yes. From anode to cathode through the external wire. Just remember that ski slope, always top to bottom.
Rule number 3.
Don't forget the salt bridge.
We can't just draw a wire, we need the bridge.
Exactly. And you must state that it allows anions to flow toward the anode and cations toward the cathode.
Mm-hmm.
If you don't use the phrase maintaining electrical neutrality, you might lose marks.
Right. Internal circuit neutrality. Got it. And rule number 4,
Galvanic equals spontaneous.
it produces energy, it does not consume it.
Correct. It is a generator. The delta G value is negative.
Fantastic. Those are the pillars. If you have those 4 down, you can handle almost any theory, question, or derivation based on this topic.
Absolutely.
Before we wrap up, I just want to touch on the history for a second, because we take all this for granted. But there was a time when portable electricity must have seemed like magic.
It was. Before the year 1800, if you wanted electricity, you had to, rub some amber to make static? Or wait for a lightning storm? You couldn't just put it in your pocket?
And then comes Alessandro Volta.
Yeah. Yes. In 1800, he built what he called the voltaic pile. It was just a stack of zinc and copper discs separated by cloth soaked in brine. But it was the first time humans had a continuous flowing source of electricity. It changed everything.
From Volta's pile to the lithium-ion battery in my laptop, the basic principle is the same.
The chemistry gets a lot more complex, but the principle of a spontaneous redox reaction creating electron flow is identical.
So let's quickly recap what we've covered in this deep dive.
We started with the observation. The Daniell cell. Zinc dissolves, copper grows, and the blue solution's color fades.
And we explained the mechanism. Oxidation at the anode, which is negative, and reduction at the cathode, which is positive.
We visualized it with that ski slope analogy.
Yeah.
Electrons sliding from a high potential to a low potential, doing useful work along the way.
And we really emphasized the role of the salt bridge in keeping that traffic flowing by balancing all the charges.
And finally, we realized that batteries die because they run out of chemical fuel. They just reach equilibrium.
You know, I'm really going to look at my TV remote differently now. Every time I change the channel, I'll picture those little zinc atoms sacrificing themselves, jumping off the cliff so I can watch Netflix.
That is literally what is happening. It's a tiny chemical sacrifice for your entertainment.
Before we sign off, do you have one final thought for our listeners? Something for them to chew on?
I do. I want you to think about this. A battery doesn't make energy. It's not some magic box. It is simply a storage container for chemical instability.
Instability?
Yes. We take these unstable chemicals that desperately want to react with each other. We keep them separated, and then we control when and how they get to react. We aren't creating power. We are just allowing nature to finally do what it wanted to do all along.
Letting chemistry do what it wanted to do all along. I love that. It makes science feel less like a set of rules and more like a flow.
It is all about flow.
Well, thank you so much for breaking this down with us. And to our listeners, keep visualizing those electrons, use that lone trick, and good luck with your prep.
Keep learning.
Thanks for listening to The Deep Dive. We'll catch you in the next one.